All right, so for lesson 10 here in 1060, we are going to be going through even and odd identities, and we're going to go through the sum and difference identities. Now, with these identities, guys, you want to remember these are things that you're going to have to memorize. So make sure you're finding tricks that allow you to memorize these. So first of all here, an odd function, right? We know this from college algebra here, 1050. An odd function is a function for which f of negative x equals negative f of x. So in other words, the opposite. And an even function is one that says f of negative x equals f of x. So the same y value when you plug in the opposite. The graph of an odd function is symmetric around the origin. So remember, it does that rotation. So like x cubed. And the graph of an even function is symmetric with the y-axis. So think of x squared. Of the 6 trig functions, cosine and secant are even functions. Okay, even in yellow. So cosine and secant are even. And the others are odd. So as you can see, sine, tangent, cotangent, and cosecant are all odd functions. So the negative theta on the inside is comparative to the negative of the whole function. Whereas the negative theta on the inside for cosine and secant gives us a positive, or it's the same as normal positive cosine secant. Okay, and we're going to use these identities to be able to simplify expressions. Okay, so the even odd identities are readily demonstrated using any of the common angles noted in section 2.2. Their truly utility, however, lies in computation, but in simplifying expressions involving the circular functions. So we're going to see how all these expressions can be turned into something else, okay? So here we have 2 binomials. So of course, the first thing here, I look in the binomials, is we have 1 plus sine x. That looks nice. But this 1 plus sine to the sine of negative x, this negative x is a little confusing. So I want to change it using the even odd identities. And I know that a negative x on the inside just is the same as a negative sine. So I'm going to change this. What I'm going to do with you guys this time is, as I'm writing each step, I am actually going to write down the justification of the step we took. So that means 1 minus sine x. So I'm using even odd identity. All right, my next step. Well, I have my 2 binomials, they don't look kind of crazy anymore. So what I'm going to do next is I'm going to FOIL. But as you can see, guys, this is the difference of 2 squares, right? Because we have the same thing, just the sign is different. So that comes out to 1 minus sine squared of x. So again, I'm going to justify what I did. I pretty much FOILed. Okay. Well, 1 minus squared x, well, that seems familiar. If we use the Pythagorean identity of cosine squared plus sine squared equals 1, we can actually flip this around, right? So this equals cosine squared of x. And of course, that's my Pythagorean identity. And I'm going to abbreviate that. If you need to, write it all out. And we're done. So crazy that this big thing right here could just be cosine squared. So let's do the same thing with b here. So the first thing I'm going to do, because I don't like the negative x on the inside, is I'm going to use my even and odd. So cosecant is an odd function, so that gives me negative cosecant of x. And tangent is also odd. What I'm going to do, guys, is just put down this negative tangent, even though we know a negative times a negative is a positive. So we did even and odd. Okay. Now I'm going to put down the step that a negative times a negative is a positive. So you get cosecant x times tangent x. Okay, I'm just going to do negatives. I'm going to say negative so we can think of negative times a negative. Now, actually, what can I do from here? Because you can go further if you really wanted to, especially since the idea is we want to get down to one simple trig function so we can play with it a little bit. So the next thing I'm going to do is I'm going to use my reciprocal. So cosecant is 1 over sine, and tangent is sine over cosine. So just to remind myself when I'm using reciprocals. Okay, my next step, and I'm going to go right up here, so since I'm running out of the room, I'm going to cancel. So I end up with 1 over cosine. So sine over sine is 1. So I think of it as canceling, but really sine over sine is 1. That's why I'm putting it in parentheses or quotes. Now, what's 1 over cosine? Well, I can do that by using the reciprocal, which is secant. And we're done, right? So cosecant negative x times tan negative x is the same as secant. We would have known. Okay, let's do the next one. Let's change our even and odd. Now remember that cosine of negative x is the same thing as cosine of x, since it's even. Okay, what did I do? I did even odd. Now we have two fractions, guys, right? Well, we can only add two fractions if we have common denominators. So let's put in that common denominator. I'm going to kind of put this all together where I'm doing the common denominator and putting it together all at once. So hopefully you can see that transition. So on this left function, we're missing a 1 minus cosine x. Okay. On the right side, we're missing a 1 plus cosine x. I'm going to put that in parentheses just in case, not just in case, but for future reference, because if this was subtraction, I would have to distribute it. So right now I'm just dealing with the numerators. You guys see that? So here I would be missing the 1 minus cosine x. So whatever I do to the bottom, I have to do to the top. Well, that times 1 is itself, so on and so forth. This is all over the common denominator now of 1 plus cosine x times 1 minus cosine x. Let me note what I just did. I did common denominators. Okay. Next, what I'm going to do is I'm going to, on my numerators, combine like terms, and in my denominator, I'm going to do that FOIL. Because again, that's the difference of squares it comes out to be. So I get 2, and what do you know? Cosine, negative cosine x and cosine x, they cancel, so I'm left with 2 on top. And on the bottom, I'm left with 1 minus cosine squared of x. So here, I combine in like terms, and I FOILed on the bottom. And for my last step, because can you guys recognize this 1 minus cosine squared x? That's the Pythagorean identity. So 2 over sine squared x. Pythagorean, I don't know why I said Pythagorean theorem. Pythagorean identity. Crazy, guys. Okay, now could we go further with this if we wanted to? Yeah, we could do a reciprocal there. We could do whatever we want. So it depends on how far we're supposed to be going, because that helps us with the next one, which is proving. So we're verifying identities. We're saying one side is equal to the other. So this section ends with a proof of a trigonometric identity, saying that, hey, this is an identity and this is an identity. So how can we show one into another? Looking back at section 2.4, where we began verifying identities, we can now add even and odd identities to the Pythagorean reciprocal and quotient identities as a tool in proving other identities, okay? So we're just doing our proving. Luckily for us this time, we're not doing the homework. Remember, the homework was kind of messy. Oops, sorry guys, let me pause. Sorry, the light. Okay, so with proving, remember one side into the other. We want to only work with one side if possible. That's the easiest way to do it. And if you remember from the other lesson, you want to deal with the side that looks the biggest, because it's easier to go from a big to a little than a little and kind of expand that, right? So first with this, we're going to work with this right side. I mean left. I'm terrible at my directions today, guys. All right, so let's see what we can do. Well, first of all, what I want to do is rewrite this so we can see this in a different format, okay? Especially with the squares, because we're going to be dealing with those. And I want you to keep in mind what's actually squared. So I'm actually going to give myself some more space. So I'm going to rewrite this as sine of negative theta squared minus cosine, oops, I forgot this other parenthesis, cosine negative theta squared all over our sine theta negative theta minus cosine negative theta. So all I did in this first step, guys, is I rewrote it. Rewrite. Okay, now I'm going to use my even and odd function, so I don't have to worry about that negative theta. Sine is an odd function, so let's keep in mind that's negative sine of theta, and that whole thing is squared, minus, well, cosine's even, so that just gives us a cosine theta squared all over, that's odd, so negative sine theta minus, that's even, so cosine theta. That is even odd. All right, what can we do next? Well, if you look here, I can change this, right? Because if we're squaring a negative number, it comes out positive, okay? So I'm going to do that first. So I get sine of theta, that whole thing squared, minus cosine of theta squared all over negative sine theta minus cosine theta. So here I'm just dealing with those negatives again, okay? All right, what can I do next? Well, if you realize on top, we actually can expand this, right? We can factor, and this is the difference of two squares. So our numerator is the difference of two squares. So we get sine theta plus cosine theta times sine theta minus cosine theta all over. What I'm also going to do in the denominator is also factor out. So I'm factoring both of these. I'm going to factor out a negative here. So if I factor out a -1, I get sine theta plus cosine theta. You guys see why I did that? So here on top we have difference of squares. And on the bottom we factor that negative. Just writing down what we did, sorry. Lost my pencil. All right. What can we do next now? We can cancel, right? We can simplify. If you look, those two cancel. So we left with sine theta minus cosine theta over -1. And that is our simplifying. Now remember, our ultimate goal is to look like on the right side of that equation. And we're a little bit backwards, right? I have sine minus cosine, but since it's over -1, that changes our signs. So it changes our sign to a negative and changes our cosine to a positive. So let me just put that positive cosine in front because it's positive. Sine is now negative because I divided by that -1. And what do you know? We got our identity. Pretty cool. All right, our next section is our sum and differences. Before we begin, let's take a moment to sketch the first quadrant of the unit circle. The reason why is we are actually going to use these values in the unit circle to help us evaluate the exact value of these kind of crazy degrees and radians. So instead of me taking time to write that, I'm going to show you that right there. Take a moment, pause if you need to, write it down, or pause it and see if you could do it yourself. All right. I also put the coordinates down. Now, don't forget the coordinate pair is x, comma, y. And of course, tangent is y over x. Let's keep that in mind. That will come up later. Okay. So here are some differences. If you want proofs on this, you can just go in your book and see how they get it. But for now, I'm going to skip all that and do the exact value. So these are ones you're going to have to memorize, guys. So with cosine, one of the things to do with cosine is just remember that cosine changes the silly sign. Okay. In other words, if we see cosine of alpha plus beta, it's going to be subtraction in our identity that we're going to use. The idea is we're not going to use our calculator anymore with this. It has to be exact. Okay, so cosine alpha plus beta is cosine alpha times cosine beta minus sine alpha sine beta. Same thing down here with the subtraction. It just turns into addition. So now we can do these crazy degrees that aren't nice on the unit circle, but we're going to use it. So cosine of 15 degrees. How can we get 15 degrees? Well, cosine of 15 degrees is just 45 minus 30. So the idea is we're going to use our special right triangles, I guess we can say, or special angles to help us with these weird degrees so we can do it without a calculator. So stick with your, sorry guys, your 45s, your 30s, your 60s, even your 90s, okay? So now we have a subtraction. So now we're going to write that down. That means this is cosine. This is going to be our alpha. This is going to be our beta. So cosine of 45 times cosine of our beta, which is 30. Now it's the opposite sign, so plus sine of our alpha, which is 45, sine of 30, which is our beta. So we have it set up, and now this is the whole purpose of our doing our unit circle, is cosine of 45 is the square root of 2 over 2 times the cosine of 30, which is the square root of 3 over 2, plus sine of 45 is the square root of 2 over 2, and sine of 30 is 1/2. Okay, love the common denominators, right? And think of your multiplication, no, you have to multiply those. So we get right now the square root of 6 over 2 plus the square root of 2 over 2. We can simplify it more by saying the square root of 6 plus the square root of 2. We can't put those together, guys. They need to be that same radicand. And 2. And we're done. Okay. Now, degrees are kind of easier to recognize than radians, okay? And there's different ways that we can do the radians, but I'm going to tell you right now, the best way to do it is change your radians into degrees because you can actually see it better. Otherwise, you're going to have to manipulate your pi over 4s, pi over 3s, pi over 2s, pi over 6s to see if you can get to 7 pi over 12. Some are going to be easier than the other. You can figure out which way you like best. But if we change this to degrees so I can obviously see what's going on, 7 times 180 divided by 12 comes out to 105. This allows me to see that, hey, to get to 105, I can do 45 plus 60. Now, yes, even though I'm using my degrees to see that calculation, I'm in radians. So I have to make sure that I'm looking at this in radians. So this is cosine of 45. So in other words, 45 is pi over 4 plus pi over 3. Okay, and now I can use my identity here, and instead of me writing it all out, I'm going to show you. Okay, so I get cosine of pi over, oh, and I switched these, sorry guys. You could do it either way you want. It comes out to the same thing. It's up to you. But as you can see, cosine pi over 3 times cosine pi over 4, so alpha beta, minus sine pi over 3 times sine pi over 4, alpha beta. Use my unit circle, so I get 1/2 times the square root of 2 over 2 minus square root of 3 over 2 times square root of 2 over 2. Combine those together, we get square root of 2 over 4. Oh, did I calculate wrong before? Oh, let me finish this. And then I put it together, and I get my square root of 2 minus square root of 6 over 4. You guys see what I did here? I totally forgot to multiply the denominator. It's early, guys. So 4, 4. And then common denominator, we keep as 4. I hope you guys caught that before I had to. All right, we good? All right, so now we're going to verify this identity. So this is a new identity we're working with. In other words, yeah, it's a new identity, but we can use our difference of cosine for the difference for cosine to prove this, okay? So the question is, does cosine pi over 2 minus theta, is that the same thing as sine of theta? And it is, and we're going to show you. Remember, start with the left side because it's more complicated. We're going to use the difference identity for cosine to figure this out. So this is our alpha, this is our beta. So we have cosine of pi over 2 times cosine of theta. Now we're going to add, because remember opposite, sine of pi over 2 times sine of theta. Okay, there's our difference. Now cosine of pi over 2 is 0 times cosine of theta, because we don't know what theta is, plus sine pi over 2 is 1. And what do you know, guys? Anything times 0 is 0, so that goes away. And anything times 1 is itself. So we're just left with sine of theta, which of course is what we were trying to prove. So this is an identity that we can use in the future. And what do you know? Here are all the rest of the identities that includes. These are called co-function identities. Okay, so these are going to be useful also. But the truth is, guys, if you had to, we can look at it as the difference to help us prove this. But we can prove all these in our text if you want to see how they go. Now let's do some sum. The sum with sum and difference. Sum and difference with sine. With sine, your sign does not change. So addition stays addition. Your subtraction stays subtraction. What changes though, remember with cosine, we were doing cosine, cosine, plus or minus, sine, sine. Now we're doing sine, cosine, cosine, sine. So look at the difference and see how you're going to memorize this. Sine alpha, cosine beta, plus cosine alpha, sine beta. So they switch. Again, we're dealing with the radian here. We could do this the hard way and try to figure out the common denominator and how to separate, or we can think of it as our radian, which of course I don't have my calculator and I did not write it down. So give me a moment. All right, so if you change this into degrees on your calculator, you find out you get 285. Which you know it's not a full rotation since this would be 24, which is 2 pi. Okay, so let's imagine where this looks on our unit circle. Okay, this means that we are in the 4th quadrant. Okay, now the only way, of course, to get our 85 is to make sure we have 45 in there. So what do you know? If you took 285 minus 45, we get 240. And 240 is on our unit circle. And that, of course, is our 4 pi over 3. And then we're adding our 45 of pi over 4. So you see how working with degrees is a little bit easier to see how it's separated. If we want, I can show you little tricks later one-on-one how to do it with radians in our common fractions. But here we got to remember it, and I'm just going to show you this work so it's easier and you don't have to see me write, that we are using the addition or sum of sine. So we're going to go alpha plus beta, and then we're going to plug in our spots. So I see sine of 4 pi over 3 times cosine of pi over 4 plus cosine over alpha, which is 4 pi over 3 times sine of pi over 4. Use our unit circle. Now remember, we are in the 4th quadrant, so that means for 4 pi over 3, we are in, am I correct here? Yes, 4 pi over 3 is in the 3rd quadrant, and in the 3rd quadrant, both of our sine and cosines are negative, so be careful. And our 45 is in the 1st quadrant, so both of them are positive. So this is why we get negative square root of 3 over 2 times square root of 2 over 2 plus negative 1/2 times square root of 2 over 2. So either you can think of it as quadrants and remember if they're going to be negative or positive, or you can just draw out your full unit circle and you have everything right there. Okay. So when we do that math, and of course I did it again down here, when you multiply through, it's over 4. And when you combine, or when you're able to combine those fractions, we get negative square root of 6 minus square root of 2 over 4. Okay, give you a moment to write that down. You can pause it if you need to so I can move forward. My nose is running, sorry guys. All right, next, find the exact value of sine alpha plus sine, or plus beta. Sorry guys, I had to pause the video and I forgot what I said last. So find the exact value of sine theta plus beta. Okay, so we're doing the sum of sine. If, so we already have alpha, sine alpha is negative 3 over 5, and cosine beta is negative 1 over 3, with alpha in the fourth quadrant and beta in the third. Okay, so what does that tell me? Let's do little by little. Well, if alpha is in the fourth quadrant, that means sine is negative, cosine is positive. That helps us because sine is negative right there. And beta in the third quadrant means sine is negative and cosine is negative. Okay, so this is a good start here. Now, what can we do though, since we already have alpha, sine alpha, but we don't know what alpha is. So how can we find cosine alpha? Well, we can use our identities, our Pythagorean identities. Okay, so what I'm going to do is I'm going to do some notes for myself. I need cosine alpha. So how I'm going to find that is actually using the Pythagorean identity of sine alpha squared plus cosine alpha squared equals 1. And now I can solve for it, right? I can say now cosine squared alpha. Now don't forget to use common denominators and all that stuff, because even though I'm adding 3/5 over, I'm adding it to, or no, I have to square it first. Ooh, crazy pants right there, right? So let me write one more step here. So negative 3/5 squared is 9 over 25 equals 1. Now let me do that algebra. So I get cosine squared alpha equals, well, if I bring that over there and now I'm actually subtracting it, I get 16 over 25. And then to take the square root, right, of both sides, I get cosine alpha of 4 over 5. Now, when we take the square root, usually we have a positive and a negative. But I know because alpha is in the fourth quadrant, cosine is going to be positive. So I will just keep that as positive 4/5. Now, for here, beta, I need sine of beta. So I'm going to do the Pythagorean identity again. This time I'm going to go sine squared beta plus cosine. So this negative 1/3 squared, don't forget it, right? Equals 1. Do that next step. So sine squared beta plus 1/9 equals 1. So sine squared beta equals 8/9. Okay, here we got to be careful because when we take the square root, we actually have to simplify that square root, right? Because the square root of 8 equals 2 square root of 2 over 9 here. Now, if we go back here, because it's plus and minus, and I'm going to figure out which one I want. I want the negative. So I'm going to put the negative there. And now I can do my sum of sine. Okay, and I'll show you that work here. So the sum of sine here would be sine alpha cosine beta plus cosine alpha sine beta. So we already knew sine alpha was negative 3 over 5. We already knew cosine beta was negative 1/3. We found that cosine alpha was a positive 4/5. And we found out that sine beta was negative 2 square root of 2 over 3. And then we do that multiplication there. So we get 3/15. Now I have a minus here because I have a positive times a negative, which of course is a negative. 4 times 2 square root of 2 is 8 square root of 2. And 5 times 3 is 15. Put it together, and there is our answer. All right. We have another one that we practiced here. Same steps. So I'm actually going to show you my written steps out and just explain all of them, just so we can go a little further. Okay. So right here, we're getting alpha is in quadrant 2. Alpha in quadrant 2 means sine is positive, sorry, but cosine is negative. So I wrote that down there. Beta is in quadrant 3, which I know that in quadrant 3, sine and cosine are negative. But a little tricky part here, they give us tangent. So how are we going to use that? Well, let's get alpha done first, because that's exactly what we did on the other side, right? Is we did our Pythagorean identity. Now I kind of skipped some steps in here just because we'd done that on the other problem. Okay, so 5 over 13 squared plus cosine squared alpha equals 1. When we do all that algebra, we get 12 over 13, positive and negative, but we're in the second quadrant, so cosine's negative, so that's where I got the negative 12 over 13. Okay, now what do we do with that beta? Well, again, cosine and sine are negative, so I want to keep that in mind. But since we have tangent, that means, yes, still use a Pythagorean identity, sorry, but we have to use it with tangent. So what Pythagorean identity with tangent is going to help us? Well, that was going to be 1 plus tangent squared beta equals secant beta. How's that going to help us? When we figure out the secant, we can actually do the reciprocal, so we can use it as cosine. Okay, so I get 1 plus 2 squared, which is 4, equals secant squared. So 5 equals secant squared, square root. And we know that since cosine is going to be negative, I put the negative in there. So we get negative square root of 5. But we remember, we have to flip that to make it cosine, which is negative 1 over the square root of 5. Now I want to actually simplify that out more and get rid of that square root in that denominator, giving us negative square root of 5 over 5. Okay, now I can actually solve for sine, because don't forget, I still have to solve for sine there. Now I can use our Pythagorean identity of sine squared plus cosine squared equals 1. Okay, I squared the square root of 5 over 5 and got 5 over 25, giving us sine of beta equals negative 2 square root of 5 over 5. And then we can use our difference of sine by going through our steps, being careful of our negative numbers, and being able to simplify that out. Okay, now we have our sum and difference identities of the tangent functions. We're going to do the same thing as we did with sine and cosine when it comes to our degrees and our radians. Okay, so of course with 15, that is 45 and 30. All right, so with our subtraction here, what I want you guys to see is the difference in these identities. So it's the same on top, same sign on top, different sign on the bottom. Okay, so the tangent is actually the same, right? Except you have to look at those signs. Okay, so now when I put my 45 and my 30s in there, okay, this is our normal identity there. But when we have to look back at our unit circle, this is why at the beginning of this I said tangent of theta equals y over x. Okay, so if you remember that tangent of 45 is going to be 1 minus tangent of 30, that's 1 over the square root of 3. You also have to simplify that out. So that's why I got rid of the square root in the denominator. You get 1 minus the square root of 3 over 3. Also do the same thing for the denominator there. 1 plus, because that's part of the identity. Tangent of 45 is 1. Tangent of 30 is 1 over the square root of 3. And then we're able to simplify in doing some algebra. For the numerator and denominator, the next step I did was find a common denominator. Okay, so make that note so you guys can keep that in there. After I found the common denominator, I'm able to put it together. Now, of course, when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So we are able to simplify that even more into this. With B, the radians, again, 5 times 180 over 12 is actually 75. So how do I get 75? That's 45 plus 30. 45 is pi over 4 plus pi over 6. So that's where I get that. And then I do everything again, and I put it in the identity. I then calculate it with my unit circle. I want to make sure that by the way, I skipped a bunch of steps because I went through the common denominator, square root of 3 over 3 stuff, and also did my simplifying. And got 3 plus square root of 3 over 3 minus square root of 3. Now, I know I went through the end of this really quickly, but I didn't want to make this super, super long. Take your time. You know how, go back to your examples, look at your steps of common denominators, multiplying, changing functions, anything like that. If you have questions, mark it down so you can ask me in class or next class, whatever you need.